The determinant, this single number assigned to every square matrix, isn't really defined by a formula. The standard formula for an n by n determinant, known as the Leibniz formula, is a massive summation over all permutations. It has n-factorial terms. For a 10 by 10 matrix, that's 10 factorial, which equals 3,628,800 over 3.6 million terms. Nobody defines the determinant that way. Instead, mathematicians define it with just 3 simple rules, and they can prove that only one function in all of existence satisfies all 3 of these rules simultaneously. Rule 1, the determinant of the identity matrix equals 1. Rule 2, swapping 2 rows flips the sign of the determinant. Rule 3, the determinant is linear in each row. These 3 axioms are all you need. Property 1, normalization, the determinant of the identity matrix equals 1. This is our starting point, that we need at least one known value to build everything else. The identity matrix, shown here as a 3 by 3 matrix with 1s on the diagonal and 0s everywhere else, represents doing nothing to space, so its determinant should be the neutral multiplicative value, 1. The determinant of I equals 1. Simple, but essential. Property 2, swapping 2 rows of a matrix flips the sign of its determinant. Let's see this in action with a simple example. Start with the 2 by 2 identity matrix with 1s on the diagonal and the 0s elsewhere. From property 1, we know its determinant equals positive 1. Now let's swap the 2 rows. Row 1 slides down and the row 2 slides up. The result is the matrix with 0, 1 in the first row and 1, 0 in the second row. This is called a permutation matrix, a matrix obtained by reordering the rows of the identity. What is its determinant? 0 times 0 minus 1 times 1 gives us negative 1. So the determinant went from positive 1 to negative 1. 1 swap, 1 sign flip. That's property 2. This idea extends to larger matrices. Start with the 3 by 3 identity matrix. If we perform one swap, say swapping rows 1 and 2, we get a permutation matrix with a 0, 1, 0 in the first row, 1, 0, 0 in the second row, and a 0, 0, 1 in the third row. Its determinant is negative 1, shown in red, because one swap flips the sign once. Now, if we perform 2 swaps starting from the identity, first swapping rows 1 and 2, then swapping rows 2 and 3, we get the permutation matrix with 0, 1, 0 in the first row, 0, 0, 1 in the second row, and 1, 0, 0 in the third row. Its determinant is positive 1, shown in green, because 2 sign flips cancel each other out. This leads to a general classification. A permutation is called even if it takes an even number of swaps to produce, and odd if it takes an odd number. Even permutations always have determinant plus 1. Odd permutations always have determinant negative 1. And importantly, the parity of a permutation, whether it is even or odd, is always well defined. This is a proven theorem in algebra. Property 3, the determinant is linear in each row separately. And so this has 2 parts. Let's look at part A, scalar multiplication. If you multiply one row by a scalar t, the determinant scales by t. All other rows stay frozen. Here's an example. Consider the matrix with first row 6 and 4, and the second row 1 and 3. Notice that the first row, the vector 6, 4, equals 2 times the vector 3, 2. So by property 3a, the determinant equals 2 times the determinant of the matrix with first row 3, 2 and second row 1, 3. Now we compute 3 times 3 minus 2 times 1 equals 9 minus 2, which is 7. So we get 2 times 7, which gives us 14. Let's verify directly. 6 times 3 minus 4 times 1 equals 18 minus 4, which equals 14. It checks out. Part B, row additivity. When one row of a matrix is the sum of 2 vectors, the determinant splits into a sum of two determinants, each keeping the same frozen rows unchanged. Let's see how this works. Take the matrix with first row 3, 4, and second row 4, 5. We can write the first row as the sum of the vectors 1, 3, and 2, 1, since 1 plus 2 is 3 and 3 plus 1 is 4. By the row additivity property, the determinant splits into the determinant of the matrix with first row 1, 3, and second row 4, 5, plus the determinant of the matrix with first row 2, 1, and second row 4, 5. Notice that the second row, 4, 5, stays frozen in both matrices. Now let's compute each determinant. The first gives 1 times 5 minus 3 times 4, which is 5 minus 12, equal to negative 7. The second gives 2 times 5 minus 1 times 4, which is 10 minus 4, equal to 6. Adding these together, negative 7 plus 6 equals negative 1. Let's verify this directly. The determinant of the original matrix, 3, 4 over 4, 5, is 3 times 5 minus 4 times 4, which is 15 minus 16, and that also equals negative 1. The results match, confirming the row additivity property. Now, here's where most people go wrong. Students see linearity and guess that the determinant of a plus b equals the determinant of a plus the determinant of b. This is false. Let's prove it with a counterexample. Let a and b both equal the 2 by 2 identity matrix. The determinant of a equals 1 and the determinant of b equals 1. Now, a plus b is the matrix with 2, 0 in the first row and 0, 2 in the second row. And the determinant of a plus b equals 2 times 2 minus 0 times 0, which is 4. But the determinant of a plus the determinant of b equals 1 plus 1, which is only 2. 4 does not equal 2, so the guess is wrong. The key issue is this: adding entire matrices changes every row at once, but property 3 only permits decomposing one row at a time, with all other rows held fixed. Right? That's why it doesn't extend to full matrix addition. Here's the payoff. The three axioms produce the familiar 2 by 2 determinant formula. Start with a general matrix, first row A, B, second row C, D. Apply property 3b to row 1. Right? The vector a, b splits into a, 0 plus 0, b. So the determinant becomes the determinant of the matrix A, 0 over CD, plus the determinant of the matrix 0, B over CD. Now apply property 3a, factor a from the first term's top row, and b from the second. We get a times the determinant of 1, 0 over CD, plus b times the determinant of 0, 1 over CD. Now we apply the same decomposition to row 2 of each term. The vector c, d splits into c, 0 plus 0, d. This sets us up to apply property 3b again, this time to the second row. After factoring out all the scalars, every determinant we're left with has rows that are standard basis vectors. Here are the 4 determinants we need to evaluate: the determinant of the matrix with rows 1, 0, and 1, 0. The determinant of the matrix with rows 1, 0, and 0, 1. The determinant of the matrix with rows 0, 1, and 1, 0. And the determinant of the matrix with rows 0, 1, and 0, 1. Now here's a crucial fact. Any matrix with 2 identical rows has determinant 0. Right? Why? This follows from property 2. Swapping 2 identical rows flips the sign of the determinant, but the matrix doesn't actually change. So the determinant equals its own negative. The only number that equals its own negative is 0. So the first and fourth terms, which have repeated rows, vanish. 2 terms survive. The first surviving term is a times d times the determinant of the identity matrix. The second surviving term is b times c times the determinant of the swap permutation matrix. Now we apply our axioms to evaluate these. Property 1 tells us the determinant of the identity is 1. Property 2 tells us that swapping the rows of the identity flips the sign, giving negative 1. So our final result is a times d times 1 plus b times c times negative 1, which gives us ad minus bc. The famous 2x2 determinant formula emerges purely from the axioms alone. This logic scales to any matrix size. Want to apply linearity to row 3 of a larger matrix? Use property 2. Swap row 3 to the top, apply property 3, then swap back. The sign flips cancel out. The 3 axioms compose together to handle every situation. Now step back and see the bigger picture. Let's restate our 3 axioms one final time. Axiom 1, the determinant of the identity matrix equals 1. Axiom 2, a row swap flips the sign. Axiom 3, the determinant is linear in each row. These 3 axioms are a specification. They declare what the determinant must do without prescribing how to compute it. Everything else is a consequence. The AD minus BC formula, derived from the 3 axioms, cofactor expansion, derived. The product rule that the determinant of AB equals the determinant of A times the determinant of B, derived. The fact that the determinant equals 0 if and only if the matrix is singular, derived. Row reduction methods, derived. Even eigenvalue computation, derived. All of these are computational strategies that satisfy the specification. This is how modern mathematics works. Define objects by their essential properties, then derive everything else. The next time someone asks, what is the determinant? Don't recite a formula. Tell them it's the unique function that starts at 1, flips on a swap, and is linear in each row. Everything else follows.